Okay, good morning. In today's session, we will be discussing about the stresses induced on oblique planes due to simple shear stress. In the previous two lectures, we have discussed about stresses on oblique plane due to uniaxial forces and biaxial forces. Okay, uniaxial forces, that is direct forces, direct stress. Okay. Also, we have discussed, what are the stresses developed on oblique plane, making an angle theta with the axis of stress, the line of action of stress. So, the stresses developed on an oblique plane due to this uniaxial force, direct forces. Okay. Also, we have discussed about biaxial forces. When stresses are acting on two mutually perpendicular directions, in two mutually perpendicular directions. So, sigma 1 and sigma 2. In this case, what are the stresses developed on an oblique plane? That is normal and tangential stresses developed on oblique plane. Okay. In this session, we will be discussing about the stresses developed on an oblique plane AB due to simple shear stress subjected to simple shear stress. When a body is subjected like this to simple shear stress, there will be complementary shear acting on the perpendicular planes to keep the body in equilibrium. Okay. So, when it is subjected to a shear stress of tau xy, there will be a complementary shear of same magnitude tau xy acting on perpendicular planes, mutually perpendicular planes. Okay. Now, in this, we will consider the free body diagram of the wedge ABC, wedge shaped element ABC. So now the stress acting on the face AC is tau xy, and on the face BC is also tau xy. Okay. So due to this, what will be the stresses on an oblique plane? Okay. Now, the convention that we are following is tau xy will be taken as positive. Okay. When it is clockwise. Okay. And also angle theta is angle of oblique plane with the x direction. Okay. So now, what will be the stresses acting on an oblique plane? For that, we consider this inclined plane. Okay. So now we have the stress tau xy on faces AC and BC, isn't it? Tau xy we have. So due to this, the force acting on this, tangential force, due to this, or that is tangential forces causing this stress. Okay, that is P1. Let it be P1, which acts vertically. Okay, so the force on AC is vertical. That is the tangential force on AC is vertical. Similarly, tangential force on BC, let it be P2, is horizontal. Okay. So what is P1 and what is P2? P1 is the stress multiplied by the area of the face AC. Okay, so area means AC into the dimension perpendicular to the plane, which is taken as 1 unit. So AC into 1 will be the area, and tau xy multiplied by it gives P1, the force acting vertically on face AC. That means it is tangential to AC, causing shear stress on AC. Okay. Similarly, the force P2 causing this on BC will be given as tau xy multiplied by area BC into 1. Okay. So P1, P2. P2 is horizontal. That is clear. Okay. P2 is horizontal. Now, what are the forces acting on inclined plane AB? Let Pn be the normal force on AB. Pt is the tangential force on AB. Now, this inclination is theta, and this is 90 minus theta. Okay. Now we resolve the forces. We have to resolve the forces along x direction. Okay. That means horizontally and vertical. We have the forces horizontal and vertical. We have to resolve them along the direction of Pn. There is normal force, and along the tangential force Pt. Okay. So what are the forces or components of P1 and P2 in the direction of Pn? Okay. So we have P1 and P2, horizontal and vertical forces. Okay. So what are the components of this in the direction of Pn? So now Pn is given as P1, this angle is theta, isn't it? P1 cos theta plus P2 cos 90 minus theta or sin theta. Okay. This is the normal force acting. Similarly, we will find tangential force. What is tangential force? P1 sin theta minus P2 cos theta. Because these two directions are opposite, one is upwards, one is downwards. The component of P1 is upwards and component of P2 is downwards. So opposite in direction, so we will take negative sign here. The net force along the tangent is P1 sin theta minus P2 cos theta. Okay. Yeah. P1 cos theta plus P2 sin theta. This is the normal force on inclined plane AB. Now we replace P1 and P2. P1 is tau xy into AC and P2 is tau xy into BC. Okay. So Pt is P2 sin theta minus P1 cos theta. Similarly here, we replace P1 and P2. So these are the normal and tangential forces acting on inclined plane AB. Okay. So what will be the stresses now? Normal stress sigma n is force Pn divided by area of AB. Area of AB is also AB into 1 unit, perpendicular dimension to the plane of is 1 unit we are considering. So AB into 1 will be the area. Pn divided by AB will be the normal stress sigma n. Okay, so Pn is just now we have seen tau xy AC cos theta plus tau xy BC sin theta divided by A. Now AC by AB from the triangle ABC here, this angle is theta. What is AC by AB? That is nothing but sin theta. Similarly, BC by AB, BC by AB is cos theta. So AC by AB is sin theta. So tau xy sin theta cos theta. This term becomes tau xy sin theta cos theta. This term becomes tau xy cos theta sin theta. So the net stress will be 2 times tau xy sin theta cos theta or tau xy sin 2 theta. This is the normal stress on an inclined plane AB due to simple shear tau xy. Okay. And how about tangential stress tau? Tangential stress tau acting on this, that is tau xy PT by AB, because tangential force PT is just now calculated, which is tau xy BC sin theta minus tau xy AC cos theta. Okay, so BC by AB is cos theta. Okay, BC by AB is cos theta. And this is not correct. It is P1 sin theta minus P2 cos theta. P1 sin theta minus P2 cos theta. So P1 is tau xy AC sin theta and P2 is tau xy BC cos theta. Okay, so tau xy AC sin, this is okay. This tau xy AC sin theta and tau xy BC cos theta. This one. Okay. So now AC by AB is sin theta. So tau xy sin square theta and minus tau xy BC by AB is cos theta, isn't it? BC by AB is cos theta. So tau xy cos square theta. So you will have minus of tau xy cos square theta minus sin square theta, or minus tau xy cos 2 theta minus tau xy cos 2 theta. So a minus here represents the stress is, normal stress is opposite to that across AC. So now the planes of maximum and minimum normal stresses, that are the principal planes, are found by equating the shear stress to 0. So the shear stress obtained is tau xy cos 2 theta minus, that is equated to 0 to know the direction of principal planes. Okay, so by equating this to 0, you will have 2 theta will be 90 or 270, so that cos 2 theta is 0 and tau is 0. Okay, so theta will be 45 or 135. Theta will be 45 or 135. That means this angle theta will be either 45 degrees or 135 degrees. Okay. In these two cases, you will have the normal stresses only. Tau xy will be 0. That means these two are the principal planes. Okay, by definition. Is this clear? Yeah. Now let us take the case of body which is subjected to direct stress in one plane and accompanied by a simple shear stress as shown in the figure. So you consider this now. So we have the normal stress sigma x in x direction, which is accompanied by a shear stress tau xy as shown here. And this tau xy will have the complementary shear on the perpendicular planes also for equilibrium. Okay. So on planes perpendicular to AC, you will have a shear stress of tau xy. Okay. Now to know the stresses normal and tangential on an inclined plane AC, AB, we consider the equilibrium of this wedge-shaped element ABC. Okay. Now, what are the stresses acting on these planes? Let us see. So, sigma x and tau xy are the stresses acting on AC, and tau xy is the stress acting on BC. Okay. So, we will have forces in x direction and y direction on AC and in x direction on BC. Okay. So now let sigma x is the tensile stress as shown, tau xy is shear stress. Okay. Now the tangential stress acting on the face AC, vertical stress, vertical force, vertical force acting on face AC is P1, which is given as tau xy into area. Tau xy into area. Okay. And horizontal force acting on face BC. These two are tangential actually. P1 is tangential force on AC, P2 is tangential force on BC. P1 is vertical, P2 is horizontal. And what is P2? Tau xy BC. Tau xy BC. Okay. Tau xy into BC. And how about the stresses force Px due to this sigma x, or force causing sigma x, stress sigma x, okay, which is horizontal, that is Px. Okay. So Px is the force causing the stress sigma x. So what is the force Px now? Sigma x into area of AC. Sigma x into area AC. Okay. Yeah. In all this, we are considering 1 unit of thickness. Okay. Perpendicular to the plane, we are considering 1 unit dimension. So area becomes AC into 1. Okay. So Px is given as sigma x AC. Okay. Now the vertical force Py acting on AC. We have considered it as P2. Let it be Py, Px and Py. Okay, which is tau xy into AC again. And horizontal force on the face BC, P is tau xy into BC. Tau xy into BC. Okay. So now we resolve these forces along the normal and tangential to the oblique plane, along the normal and tangential to the oblique plane. So here, what are the forces that we have? On AC, we have Py. Okay, on AC, we have Py and Px. And on BC, we have force P. Okay, force P. That means horizontally we have force P and Px. In vertical direction we have force Py. Okay, understand? So here, resolving this now in the direction normal to the plane AB. So you will get Pn is Px. Px is in this direction. Okay, and this angle is 90 minus theta. This is theta. Okay, 90 minus theta. So Px will be the component of Px will be in the direction of normal, which is towards left, actually towards left, isn't it? Px cos 90 minus theta, that is Px sin theta. Okay, minus Py cos theta. Okay, yeah, this is in the direction of sigma, minus P cos 90 minus theta, that is sin theta again. So sigma x AC, the Px value is sigma x AC, and Py is tau xy into AC. P is tau xy into BC. Okay, so replace these values, and now resolving these forces in the direction tangential, okay, to the inclined plane AB. You will have the forces, the components of forces Px cos theta, Px because this angle is theta, Px cos theta, and Py. These two are in the same direction. These two components are upwards. So Px cos theta and Py sin theta both are upwards, and P cos theta is downwards. Okay, P cos theta is downwards. So again replace Pxy, Px, Py and P. You replace them. The tangential force is given by this, and normal force is given by this expression. And the stresses are given as Pn by AB. Normal stress sigma n is Pn by AB. So Pn is sigma x AC sin theta minus tau AC cos theta minus tau BC sin theta divided by area of inclined plane AB, which is again AB into 1 unit. Okay, so now sigma x into AC by AB, which is sin theta again. So sigma x sin square theta you get, and tau xy into AC by AB, that is sin theta into cos theta here. Tau xy sin theta cos theta, and this is tau xy sin theta cos theta here. So sigma x by 2 into 1 minus cos 2 theta. We can replace sin square theta by 1 minus cos 2 theta by 2. Similarly, this one, tau xy sin theta cos theta, 2 times of that. So tau xy 2 sin theta cos theta, which is sin 2 theta. Okay, this is the expression for normal stress. Expression for normal stress on the plane AB. Similarly, the expression for tangential stress PT by AB. Tau is equal to PT by AB. So PT value is this divided by area AB. So we'll get sigma x into sine theta cos theta here, and tau xy into sine square theta minus tau xy into cos square theta. Okay. So tau xy into sine square theta is 1 minus cos 2 theta by 2, and this one, or simply you can write minus tau xy into cos square theta minus sine square theta, which is cos 2 theta. We can simply write like this. This is not necessary. So you can write here tau xy into cos square theta minus sine square theta. This. So minus tau xy into, this is nothing but cos 2 theta. You can simply write like that. And sigma x sine theta cos theta can be taken as sigma x by 2 sine 2 theta. Okay, this is the expression for tau, the tangential stress acting on the inclined plane AB. Okay. Yeah. These are the two cases we wanted to discuss. Okay. Now, how about the principal planes in this case? Principal planes. Principal planes means the planes on which tau is 0, isn't it? So equating tau to 0. Okay. What will you get? Equating tau to 0. Yeah. We are taking theta as theta p, the angle at which tau is 0. Okay. Yeah. This gives tan 2 theta p is equal to tau xy, 2 tau xy divided by sigma x. Tan 2 theta p is 2 tau xy by sigma x. Okay. So now if you see, so 2 xy, case 1, you can take minus 2 xy by minus sigma x. Okay. It will make no difference. Similarly, tau xy by sigma x. Okay. 2 tau x by sigma x. In both the cases, the hypotenuse here becomes sigma x square plus 4 tau xy square under root. Isn't it? Okay. Yeah. So we have the inclinations to theta p1 and to theta p2. So now from case 1, we have sine 2 theta p1 is equal to, opposite side is here, minus 2 tau xy by hypotenuse, and cos 2 theta p1 is minus sigma x by this hypotenuse. Okay, sigma x square plus 4 tau xy square under root. And case 2 gives sine 2 theta p is 2 tau x by hypotenuse here. Similarly, cos. Okay. So this gives two sets of values for theta p and theta p1 and theta p2. Okay. So by substituting these values of theta p1 and theta p2, we will get the principal stresses. Okay. So maximum principal stress now is obtained by substituting, what is the expression for normal stress? Yeah, this one. Okay. So here substituting 2 theta p, what is cos 2 theta p here? Yeah, we can substitute this, cos 2 theta p. Okay. So sigma x by 2 minus sigma x by 2 into cos 2 theta p1, which is minus sigma x by square root of sigma x square, that is hypotenuse. Similarly, minus 2 tau x by into sine 2 theta, which is given as this minus 2 tau xy by the square root of sigma x square plus 4 tau xy square. Okay. Yeah. And then simplifying. What will you get by simplifying here? Sigma x by 2 and this is sigma x square by 2 times of this plus 2 tau xy square by this one. So adding these two, you will have sigma x square plus 4 tau x. So finally you will have sigma x by 2 plus square root of sigma x square plus 4 tau xy square by 2. And taking this 2 into the square root, you will have sigma x by 2 square plus tau xy square. Okay, and this square should be here. Okay, yes. Similarly, minimum principal stress is obtained by substituting cos 2 theta p2 here. From case 2, we substitute the values of theta p2, that is cos 2 theta p2 and sin 2 theta. Okay, you will get this expression. So here you will have plus sign and here you have minus. So this shows that this is the minor principal stress and this is the major principal stress. Okay, that's all for now. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.